a collaboration between Beyond Benign and IUPAC. This is a brief introduction to MOFs, which stands for Metal Organic Frameworks. Today, our world is facing major challenges related to air and water pollution, as well as the well-known greenhouse effect. This phenomenon is mainly, even if not exclusively, caused by our reliance on fossil fuels as the primary source of energy. The greenhouse effect is driving climate change, whose impacts are unfortunately becoming more and more evident. Imagine if there were a kind of magic sponge capable of removing all of these problems. Of course, this is just a dream, but science often turns dreams into reality, step by step, and sometimes these efforts are recognized at the highest level. In 2025, the Nobel Prize in Chemistry was awarded to Susumu Kitagawa, Richard Robson, and Omar Yagi for the development of metal organic frameworks. MOFs. But what are MOFs? MOFs are a class of materials, ordered porous materials, made of metal nodes, metal atoms or clusters, bridged by organic linkers. What makes them special is their huge porosity. They can be imagined as tiny structures with a lot of empty space inside, organized in cavities and channels. Because of all these tiny pores, their internal surface is huge. In fact, just 2 grams of a MOF can have a surface area comparable to an entire football pitch. They can be thought of as sponges with nanoscale pores that are invisible to the naked eye. Chemists can prepare thousands of different MOFs, allowing them to absorb a wide variety of molecules and opening the way to many different applications. One of the most promising applications of MOFs is capturing CO2 directly from the air, something already being tested in pilot systems. And being CO2 responsible for the greenhouse effect, its removal from air could help fight climate change, and the captured CO2 can even be reused. Thanks to their porosity, MOFs can also store hydrogen, a clean fuel that can support the transition to sustainable energy. MOFs can also be used to harvest water directly from air and to remove pollutants from contaminated water. These technologies are already being demonstrated in prototype devices, but they are still under development. Beyond environmental and energy applications, MOFs are also attracting great interest in the field of human health. MOF can act as nanostructured carriers, loading drugs inside their pores and releasing them in a controlled and targeted way, decreasing the amount of drug and optimizing their delivery in the right target. These are just some examples of the many possible applications of MOFs. Chemical and technological research on MOFs will grow in the coming years. MOFs are a powerful example of how chemistry can serve as a fundamental tool to address global challenges. If you would like to learn more about research on MOFs, a webinar recording is available via the QR code. Thank you to Beyond Benign and IUPAC for supporting the production of this video.